So today we're going to learn how to find acceleration with a position versus time graph now. First, we have to establish a key relationship between the acceleration and the position. So to begin with, acceleration is the change in velocity divided by change in time, and velocity is the change in position divided by change in time. So if we plug that in for velocity, we'll get that acceleration is the second derivative of the change in position. And this is going to be the key property to help us read the position versus time graph to get the acceleration. So we're going to have to use a key aspect of second derivatives of any function, which is that we can relate the concavity or curvature of the graph to the acceleration. So we can start by drawing a standard position versus time graph as seen below. And so we can identify some key points on this position versus time graph, which we label A, B, C, D, and E. So on a position versus time graph, the curvature tells us the object's acceleration at that point. So if the slope is concave up, then the acceleration is positive and the velocity is increasing. And if the slope is concave down at that point, then the acceleration is negative and the velocity is decreasing. And if at that point it's an inflection point, the acceleration is equal to 0 and the velocity is not changing. And below I'll show you how to identify these. So in the middle here is an inflection point, and on the left side where the slope is going from down to up, that's concave up. And when the graph is going up to down, that's concave down. Now with this second derivative tool, we can now identify what the acceleration will be at each point in the graph. So I just draw the graph again below. So at point A, it's going to be concave up, because you can see it's going from the graph's going down to up. And then at point B, that'll be an inflection point, because you can see part of the tangent is below the graph and part of the tangent is above the graph. So the acceleration is going to be equal to 0. And then at C, the curvature is actually downward, because you can see through the graph it goes up to down there. And then D will also be an inflection point, because you can see the part of the tangent is above the graph and part of the tangent is below the graph. And then with E, you can see that's concave up as well, because you can see the slope is going from down to up, and also the tangent is below the graph. So a little recap on how to identify what the acceleration will be by looking at a position versus time graph by the point. So if the point looks like this and we draw the tangent and the tangent's below the graph, it'll be concave up and the acceleration will be positive. And if the point looks like this and we draw the tangent and the tangent is above the graph, then that'll make it concave down and make the acceleration negative. If the graph looks like this and we draw the tangent and part of the graph is below the tangent and part of the graph is above the tangent, that would mean it is an inflection point and the acceleration is equal to 0.